Okay, in this video I will be deriving the Maxwell Relations. Know that you only really need to know this one, which is called the fundamental equation. So we're going to start with deriving the exact differential for u, and then we're going to derive it for all of these, and then from there it should be simple to get to the Maxwell Relations. So to get an expression for u, so the first law of thermodynamics basically states that du is equal to dq plus a dw. So consider a reversible reaction or process. So from the second law, we know that change in entropy is equal to a change in the reversible heat over T, where dq reversible is equal to T ds. We also know that the work done reversibly is equal to negative p dv. So we can substitute these expressions into the first law to get the fundamental equation. So T ds minus P dv. So that's that. To get the exact differential for enthalpy, we just use the original definition. H is equal to U plus PV. So in order to evaluate enthalpy over an infinitesimal change, that's essentially, dH is equal to du plus dPV. So that's equal to du plus VdP plus PdV. If you're curious about where that came from, I just use the product rule here, where I multiply P times dV plus V times PD in order to get dPV. So now we can substitute du, which we know to be Tds minus PdV from the first derivation. So plus VdP plus PdV. So from here we can cancel out PdV, the PdVs, and arrive at our exact differential for enthalpy. So TdS plus VdP. Right. So now we want the exact differential for the Helmholtz free energy. So we know that the definition of the Helmholtz free energy is the internal energy minus Ts. So evaluated over an infinitesimal change, dA is equal to du minus dTs, and in the same way as PV and the enthalpy equation, we get du minus TdS minus S dT. So we obviously know the equation for du to be TdS minus PdV minus TdS minus S dt. You can obviously cross out these TdS terms, and your final Helmholtz exact differential is dA is equal to minus P dV minus S dt. And I'll box that. And then the final state function is the Gibbs free energy, which is equal to H minus Ts. Evaluated over an infinitesimal change, dG is equal to dH minus dTs. That is equal to dH minus TdS minus S dt, where we know what dH is. It's equal to TdS plus VdP. So TdS plus VdP minus TdS minus S dt. So cross those out, and you get VdP minus S dt for your exact differential for the Gibbs free energy. So really don't have to memorize any of these if you just remember the first and the second law. But now that we have our exact differentials, we now want to evaluate or derive the Maxwell relation. So before that, you want to know like what exactly the Maxwell relation, like where that comes from, or what is the equation or the relation that you want to use. So say you have a function which is reliant on two variables x, y. So that would mean df is equal to the partial of f over x with y constant dx plus df over dy, constant x, and then dy. Right. So we can call these g and h, which is what I believe the textbook calls them. So now you have df is equal to g dx plus h dy. So essentially the Maxwell relation states that if you evaluate the partial derivative of g over the partial derivative of y at constant x, that is equal to the partial derivative of h over the partial derivative of x with y constant. And in order to see where this kind of come from, so I'll just break that out into one sort of term. So remember g is equal to delta or partial derivative of f over partial y x at constant y, and then you evaluate that at constant with respect to y at constant x. So that gets you is a the second partial derivative of f with respect to the partial of x and the partial of y, and then just these two kind of cancel out. So you're left with that. Notice that this also does the same thing. And that's equal to. So really, if we want to make sure that this works, or this kind of meets the criteria, if the function f meets the criteria for an exact differential, then it should be the case that these two are equal. So now that we've derived all of our exact differentials, we can go back here and kind of put in terms where this is g dx h dy, g dx h dy, g dx h dy, g dx h dy. So essentially you can use the relation the partial of g over the partial with respect to y at constant x is equal to the partial of h with respect to x at constant y. So now you can just go through all of them. So for internal energy, the partial of g, which is the t variable here, or the value here, over partial y, or partial v, at constant s. I'm not cheating, by the way, I'm not looking at the table. Is equal to minus, don't forget the minus sign, partial p over partial s at constant v. And then for h, the partial t over the partial p at constant s is equal to the partial v over the, with respect to s at constant p. I'll erase some of this, it's in my way. Okay, and then the Helmholtz partial. Okay, notice that there are two negatives, so those will just cancel out, and we can just evaluate it as a positive Maxwell relation. So the partial p over the with respect to t at constant v is equal to the partial s over with respect to v at constant t, and then for the Gibbs free energy. Here the minus sign actually does matter, so partial v with respect to t at constant p is equal to negative partial s over dv with respect to t. So now we can just double check all of them. Yeah, yep, that makes sense. So that kind of works out. And there are the Maxwell relations.